Okay, so we're jumping into section 2.2, and we're actually going to break this up into 2 days. So we'll call this section 2.2 part 1. And I'm only going to focus on these first 3 objectives for today, and then we'll tackle 4 and 5. We'll need a little bit more time to develop this idea of symmetry test when we're dealing with an equation. So I'm going to save that for our next class time. So let me give you some examples. First of all, your first block of problems will look like this. Given a particular equation, given a set of ordered pairs, you're supposed to determine which of these are actually solutions, or which of these ordered pairs actually fall on if you were graphing this equation. So you're just going to do some inputs, outputs, and the bottom line is you're trying to determine if you input 0 in for x and in this case 0 in for y, does it make the equation balance? Okay, and so that first one's probably pretty obvious. If we let y be 0 and x be 0, 0 to the 4th is 0, square root of 0, 0, this makes the equation true, so this point would be on the graph. So let's just make sure it could be that more than one of these points falls on the graph. So let's just go ahead and do a little test of all of the others. If I input 1 for y and 1 for x, I get 1 is equal to 1 to the 4th, of course, is 1, and the square root of 1 is 1. Well, that obviously is not equal, so this point is not on the graph. And I'm not going to take a whole lot of time on this last one because you can probably see ahead of time if I input -1 for x, I'm going to be doing the square root of -1, which is not a real number. Therefore, this cannot be on the graph. So those are probably pretty simple. The whole idea here is can you tell whether or not a given point falls on the graph of a given equation? So you're just going to do inputs and outputs and see if the equation balances. Is the left side equal to the right side? Okay, the instructions change when you get to the block of problems containing number 21 as an example. So these will be requiring graphs. So the instructions read like this: find the intercepts and then graph each equation by plotting points. So let's tackle this first little phrase, find the intercepts. And let's start with the X-intercept. You recall that just means if this graph crosses the x-axis, where exactly does it cross the x-axis? And the way we find an X-intercept is we replace y in this equation with 0, and then we solve. So once again, I'll just say that again. If you want to find an X-intercept, just let y be 0 and solve the equation. Okay, so I'm going to add 1 to both sides. I'm going to do the square root of both sides. So don't forget, I should be coming up with 2 solutions. And if I don't include plus minus, I'm only going to have 1. So I'll be missing an X-intercept if I don't remember plus minus here. So again, another reminder, if you do the square root of both sides of an equation, make sure you include plus minus. So I'm going to go ahead and plot as I go. I know this graph has to cross the x-axis. I found X-intercepts at +1 and -1. All right, and just following their instructions, let's find Y-intercepts. Well, it's kind of the reverse. If I want to find a Y-intercept, I let x be 0 in this equation. And that's pretty obvious that my Y-intercept is going to be -1. Okay, so I'm going to go ahead and treat this as though I need maybe just one more input, because if you probably recognize this is going to be a parabola, and with all parabolas we have symmetry around a certain line. And in this case, that symmetry occurs around the y-axis. So if I do one more input, just to have something else to draw through, so I'm going to input 2. I'm going to let x be 2 in this equation. And if I input 2, the output, or the y, should be 3. 2 squared is 4 minus 1. So I'm going to plot 2, 3. And then once again, knowing that we have symmetry means I don't have to do another input. I can just come over here on the other side of that symmetry line and put the corresponding point. And that'll be enough for this graph. Just connect with a curve. Should be a U shape. I just picked another input, something that I don't already have a point for, so you could technically pick anything you want. X, the input, is always independent. It can be whatever you choose. Y will be dependent on what you pick. So there's the graph, and it says to be sure to label the intercepts. And so I'm okay if you just do it like this. Either you can do it on the graph, or you can just say my X-intercepts are plus minus 1, 0, and my Y-intercept is 0, negative 1. So you can just label them by showing them as their ordered pair equivalents. Okay, let's just try one more of those. So same directions. Let's find the intercepts first. So Lily, how do I find, let's start with the X-intercepts. Just tell me how to find the X-intercepts. Wait, okay, replace y with 0. So when I do, 4 times 0 is 0, and that makes my equation look like this. And now I solve for x, dividing by 9 on both sides. And since I'm doing the square root of both sides, I can't forget I need to include plus minus. So it looks like I'm going to have X-intercepts at positive 2, 0, and negative 2, 0. Okay, now let's work on Y-intercepts. And so Ruthie, how do I find the Y-intercept? Over here, to get the Y-intercept, we just replaced x with 0. Yeah, so that's what you'll always do. So if you let x be 0 in the original, that just makes this term become 0. It's, in other words, it just cancels. 0 squared is 0, 9 times 0 is 0. So in essence, to find the Y-intercept, you're just going to solve this little equation. 4y is 36. And we come up with y as 9. So our Y-intercept will be the point 0, 9. 2, 4, 6, 8, 9. Okay, well, it looks like we got another parabola, but obviously if our vertex, which it looks like this is going to be the vertex, is way up here, and we're crossing these 2 points, then this is going to be obviously an upside down parabola. So let's just get a couple more points to draw through just to make it a little more precise. So we'll do a table of values. John, give me a good candidate for an input. You want to do 3? Okay. I would probably do 1 just because it's easier math, but 3 is okay. 3 might actually go off the graph. I'm not, is that possible? So let's just stick with easy math. If I do input 1, remember square first, then multiply. So this just becomes 9. And now I'm going to, I'll just go horizontally here. I'm going to subtract 9 from both sides. 36 minus 9 is 27. And I get y is 27 fourths. So since we're graphing this point, think of that as a mixed number. 27/4 would be, remember how to change those into mixed? How many times does 4 go into 27? 6, with how many left over? 3/4, 6 and 3/4. So when we input 1, we got an output of 6, and I'll just say decimal, 6 and 3/4. So let's plot those. 1, 1, 2, 3, 4, 5, 6, and it's not quite to 7. And once again, all parabolas have symmetry around what is known as an axis of symmetry, and in this case that'll be the y-axis. I missed my points, but I think you get the idea. Okay? Any questions about those types of problems? All right, so let's move on to, I've got 2 more examples. You move now into a new block of problems, and this will be the last block of problems that you'll have to do for part 1. So here are the instructions. Plot each point. So here's my given point, 3, 4. Let's go ahead and plot it. And this is just an exercise in symmetry, and we're going to be talking in more detail about symmetry with respect to the x-axis, the y-axis, and the origin. But this is really just a simple little exercise in identifying for a given point where are other points that would represent x-axis symmetry and y-axis symmetry and origin symmetry. So I'll just work through this one with you. Symmetry with respect to the x-axis means that for this red dot, just think of this red dot flipping over the x-axis, and that would put it down here with my blue dot. And I'm going to call that, of course, 3, -4. And that's answer to part A, so I'm going to put a little A beside that. So notice with symmetry with respect to the x-axis, I should be the same distance away on the same vertical line and the same distance away from the x-axis. I'm 4 units in the other direction with respect to the red dot. Okay, now let's move to y-axis symmetry. Well, here's the y-axis. If I want to create y-axis symmetry, then I move the same distance away from the y-axis on that same horizontal line. And that would be the point -3, 4. And that's the answer to letter B. Okay, for origin symmetry, that means, of course, here's the origin. I should be the same distance away from the origin, but as you can tell, that's going to be in this direction. Just think of the origin as the midpoint for this red dot and its corresponding point. So this would create origin symmetry. And that would be the point -3, -4. And that's the answer to part C. Okay. This is kind of leading into what we're going to have a discussion about on Monday. But I'm curious if there's a takeaway from this, something that you notice when it comes to looking at a given point and comparing that point with its x-axis symmetry point. Okay, notice that. Just take a little picture of it in your mind. And then compare the given point to the point that creates or is created by y-axis symmetry. What do you notice? And then origin symmetry. Just give me something that stands out to you that's maybe kind of interesting, some sort of pattern maybe. X-axis symmetry. Y-axis symmetry, origin symmetry, looking at those points. Okay, that's true. We did make a rectangle, but that won't always happen. You'll see in my next example. Isn't it kind of interesting that when I took this original point and I created another point that represents x-axis symmetry, what changed? The y. Kind of interesting. It's the opposite, right? And when I went back to this same original point and I created y-axis symmetry, what changed? The x. It became opposite. And then when I went from original to origin, what changed? Both. They both became opposite. So I know you're going to have a few days, couple of days, when you won't think about this at all, but that's a good preview into what we're going to talk about on Monday, and we're going to get a little bit deeper in this topic. But I just thought I'd introduce it to you today. All right, last example. The instructions are the same. Plot the point. All right, so here's 0, -3. And let me get some help from someone, maybe Cody. Let's do letter A. What would the point that, I will plot a point that represents symmetry with respect to the x-axis. Where would that point be? 0, 3. Very good. And I'm going to label that as letter A. That's my answer to A. Now this is interesting. This point actually falls on the y-axis. So what's the point that is symmetrical to the y-axis? Any thoughts? Yeah? It's itself, exactly. I mean, it's almost as if, think of this line splitting this actual point up. I know it's not really technically that, but it's literally splitting that point up into that point being mirror images of itself. So Stacy's exactly right. For part B, when this point actually falls on the y-axis, the point that would represent y-axis symmetry would just be itself. And then finally, part C. John, what do you think? What point would represent origin symmetry for 0, -3? 0, 3. So the answer that we got for part A is actually also the answer for part C. Okay? Any questions? No questions? All right, I'm going to let you get started. There's really not a whole lot there. And I'll be around to help if you need it. Let me know if you have any questions.